Precalculus, this is 1.3. So this is the first section that we're going over in Chapter 1, over complex numbers. This is the stuff I didn't get to finish in class today. So I just finished first period, and we didn't get any further than the beginning of example 6. So we started it, set it up, but we didn't end up doing anything with it because the class period was going to be over very soon, so I had to take attendance. So here, example 6, it says find each quotient. There's 2 of them. Write each answers in standard form, a plus bi. So what we were discussing in class, the issue here, that expression needs to be rationalized, and if we ever have an I on the bottom, we don't consider that completely simplified. We'd want to actually divide each. So if you want to think of them as a division problem, you can. But you can also think of this as a simplification of a radical expression, and there's an I on the bottom. If we have negative exponents, we gotta deal with that. If we have i's on the bottom, we also got to deal with that. Now, if there's common factors top and bottom, same idea, we got to deal with that. So how do we deal with that? The problem is there's an I on the bottom. I don't want the I there anymore. I want the number on the bottom to be a real number. And we discussed a method for changing a complex number to a real number, and that was using the sum of squares formula. If you take a complex number and multiply it with its complex conjugate, you just vary the sign in the middle, then you get a real number in return. A squared plus b squared would be real because a and b are real. So that's actually our trick within a division situation like that to get the I on the bottom to disappear. So what I do is I multiply. If I want the bottom I to disappear, I would do so by multiplying the complex conjugate of 3 plus I, 3 minus I in this situation. However, in a fraction, whatever I multiply to the bottom must also get multiplied to the top, as long as we don't have 0. So then we are going to distribute these two, top and bottom, separately. Well, the bottom, there's a shortcut for it. On the top, there's no shortcut for it really, unless I see some special pattern, which I don't. But you would have to multiply 5 minus 5i with 3 minus I. The way that we did earlier, for example, 4 and 5. So on the bottom, 3 plus I, 3 minus I. Well, 3 plus I is the same thing as 3 plus 1i. 3 minus 1i for 3 minus I. The coefficient on just I by itself is a 1. So what I'm trying to do is I'm trying to set it up for this situation where I can figure out what that shortcut's going to be. So what you do is you square the coefficients and add them. So when you see a difference of squares like this with i's for the second terms, what you do is you sum the squares of the coefficients. That would be 3 squared plus 1 squared. That would be 9 plus 1, which is 10. So you get 10 in the bottom. It's as simple as that. And then we continue with the top. So I still have to deal with the stuff on top. So then we have to distribute 5 times 3 is 15. 5 times negative I is negative 5i. And I'm doing this on a Friday morning, so hopefully I don't make any mistakes, which I already did earlier, first period. Negative 5i times 3 is negative 15i, and then negative 5i times negative I. It's going to end up being a positive 5i squared if I do this carefully, because negative negative is positive, but it's going to end up turning into a negative again. All this divided by 10. So I'm going to go ahead and combine like terms. Well, before I do that, 15 minus 5i, and this was a plus 5i, I believe. Let me double check. So that might be one of those mistakes I was talking about earlier. That was the result of taking negative 5i with positive 3. So that should be a negative 15i. Well, sometimes this thing doesn't register every thing that I'm writing. So like a plus sign, the first stroke, it doesn't register. So that might have been what happened here. Maybe, maybe not. Or I could have just completely forgotten to write it. That would be plus 5i squared, but I squared is negative 1. That would be negative 5. All divided by 10. So not completed all the way through until I got rid of that I squared quantity. So now we combine like terms, and I see that the 5 and negative 5 can combine. I get 10. Negative 5i, negative 15i will be minus 20i. And then we have a 10 on the bottom. And then what we do at this point is we deal with it just like any real number quantity. The distributive property applies here. So if you have the sum on the top with just a simple real number on the bottom, you could distribute division by that real number into both terms. So that's the same thing as 1 over 10 times 10 minus 20i. So that's going to be 10 over 10, which is 1, and then minus 20 over 10i, which is going to be negative 2i. And that's going to be it for this particular example. That's already written in standard form, a plus bi. In this case, it's a minus because the coefficient on the I term is going to be negative. Let me zoom out of that because that's quite a bit of work. So that's how we deal with division between two complex numbers. What you do is you take the number on the bottom, the complex number on the bottom, multiply its complex conjugate on both top and bottom, numerator and denominator. And then you just multiply them both out. There's going to be a shortcut for the bottom, but no shortcut for the top for the most part. Letter B. This is one of those that's a lot simpler, and it might seem very confusing to start, but it's a very easy problem. But we follow the same procedure. If I have a complex number on the bottom, you multiply top and bottom by the complex conjugate of the number on the bottom. What's the complex conjugate of negative I? So you might have already guessed, but negative I is 0 minus I, or 0 minus 1i. Its complex conjugate is going to be 0 plus 1i, or this is the same thing as negative I. This one here is I. So you might have already guessed, the complex conjugate of negative I is I. So I and negative I are complex conjugate pairs. So that's just to show that they're two complex conjugate pairs, so I and negative I. So what you do is you multiply I on both sides, or both top and bottom, numerator, denominator. And then you simplify. Multiply the numerators together, 15i. Multiply the denominators together, negative I squared, which is going to be 1. Negative I squared is negative times negative 1. Negative negative 1 is positive 1. 15 divided by 1 is 15. Oh no, I forgot the I. So there's another mistake. Yes, that didn't look right. So there's supposed to be an I here. So these two become 1, and those two become 15i. So I have to think of those separately. So that should be 15i over 1. Should be equal to 15i. And those are very straightforward. So there's the division algorithm for two complex numbers. Now before I go ahead and consider this section done, there's one more thing that we want to cover. And that's going to be powers of I. So once we've already come up with the mechanism for multiplying I, or squaring the number I, we have a mechanism for finding I to any integer power. And it actually works out, integers also include the negative exponents, which hopefully we'll see an example that's like that here. Yeah, we will. Okay, so we'll look at I to the first power, that's just the power of I. I to the first power is just like anything to the first power, it's itself, just the base. And there's a reason why. We're going to see a pattern that's going to be cyclical in nature. There's going to be a cycle. I squared is negative 1. That's by definition. Once we know both of those, we can figure out the rest here. So I don't know if I want to zoom in. I to the third power. I to the third power is the same as I times I times I, which we can group two of those together as I squared, and the next one I. And knowing this right away, we can come up with an expression for I cubed, or I to the third power. So that's I squared is negative 1 times the remaining I, negative I. So that's the expression for I cubed, negative I. So I might want to go ahead and make that smaller. Move this over to the side. Negative I is the result. I to the fourth power. Many ways you can think of this one. And the way that I'd like to think of this one, I squared squared. Because a fourth power is the same thing as a double square. So then we can simplify this. The stuff inside parentheses first, I squared is -1 according to the order of operations, and then we square it. Then we'll go ahead and deal with the exponent on the outside. So -1 squared is 1. I to the fourth power is 1. And we can keep on going. I to the fifth. The way we would think of this, the way that we would think of this one, I to the fifth is the same thing as I to the fourth times I. Because if you would think of that as the the product rule. So that first product rule that we saw, first day of class, R.3, or the second day of class, because first day of class was just the syllabus, you can separate them as the sum of two exponents, 4 and 1. 4 plus 1 is 5. And because we understand what I to the fourth is, it's 1, so that's going to be 1 times I, which in this case is just I. So we've landed back at I for I to the fifth. Now you can keep on going. I to the sixth is the same thing as I to the fourth, and that times I squared. So we end up getting just 1 times I squared, which is I squared, and that's -1. And we're back at -1. Notice how these two match. That's going to be the case of the next two match. I to the seventh is I to the fourth, I cubed. So that's just I cubed, because I to the fourth is 1. I cubed, -I. And you'll notice I to the eighth is I to the fourth times I to the fourth, which is I to the fourth, which is 1. And it goes in a cycle. If I continue the cycle, let's say I to the ninth is I to the eighth times I, which is I. I to the eighth is 1. So this is going to reveal a pattern, hopefully. Like if I wanted I to the 13th, that's going to be I to the 12th times I. So I'm choosing numbers that are divisible by 4. I to the fourth is 1. I to the eighth is also 1. And that's because 8 is a multiple of 4. So we use that here. A multiple of 4 is going to end up equaling to 1. So here's the idea. And this is a theorem. I to the 4n power, where n is any integer, is always going to equal to 1. For any multiple of 4, I to the 12th, I to the 16th, I to the 20th, I to the 24th, all of those are the same thing as I to the fourth power, because they're divisible by 4. They're multiples of 4. And what that does is it allows us to come up with a scheme for simplifying weird expressions like these. In example 7. So then, can we do this for like a random exponent, I to the 33rd power? And the answer is yes, we should be able to. You want to think of I to the 33rd power as the sum, or the 33rd power is the sum of a multiple of 4 with something else. So here's the idea. You can keep off shaving I to the fourths. So that's I to the fourth times, you subtract I to the 29th. And you can get rid of this one because this one's 1, and 1 times I to the 29th is 29. 29 is 4 and 25. So that one goes away to 1. 25 is 4 added with 21. That goes away. And you can keep on doing this over and over and over. And you're going to shave off enough 4s, and you're left with something that can't go any further. All right, so the same basic idea is, instead of just shaving off 4 at a time, why not shave off the largest multiple of 4 at the very, very beginning? What's the largest multiple of 4 that can go into 33? Added. 32, I believe. 32 is divisible by 4. And at this point, I don't care what 32 divided by 4 is. I just know that it is divisible by 4. All right, but that would be what? 32 divided by 4? That'd be 8. Yeah, so either way, that one's going to go away. That's a 1. And this one's an I that's left over. So the reason being, it's because 33 is equal to 32 plus 1, and 32 is divisible by 4. That's 4 times 8. Now I don't care what 32 is in terms of 4 times something. I just care that 32 is a multiple of 4. So you can go straight here as a shortcut. Shave off the largest multiple of 4 you can, and it'll simplify it. So then the final answer is I. Once you end up with one of these 4, the first 4, you're done. It's either I, -1, or 1, not in that order. And then we'll look at letter B, and we'll go ahead and stop. I to the -14th power. Now how do I deal with something like this? You will deal with it the way that you do any real expression. Anything with a negative exponent will get moved, and it's going to get moved under a 1. I to the +14th power. Once I'm good with this step here and changing it to something with a positive exponent expression, then we can go ahead and carry on with this procedure, just like we normally would, and then just simplify, since it's a rational expression. That's 1 over, and with the way we think of 14 is I'm going to shave off the largest multiple of 4 from that by addition subtraction. So I think that's 12. I to the 12th power times I squared, because 12 plus 2 is 14. So what happens to the multiple of 4? It goes away. It's just a 1. So we're just left with 1 over I squared. 1 over I squared is 1 over -1, which is 1 divided by -1 is -1. And that's it for that one. So this is something that will be on your next test. There'll be quizzes too, maybe, but I'm thinking about those just being practice quizzes, just like we did for the previous test. And that's going to go ahead and conclude 1.3, complex numbers. So on Wednesday, we'll continue with quadratic expressions, quadratic equations. And we might start 1.5, which are applications of quadratic equations.